does it have?
When I used 1.5 meters in class on Wednesday, I was standing around here, the textbook was about there, I said that's about 1.5 meters. What is that 1.5 meters?
The distance.
The distance between you and the object.
Okay. It's the distance, more specifically, it's the center to center distance. So if I double the radius of Earth, or if I have some planet which is twice the radius of Earth, I'm now farther from the center. And gravitational pull weakens the farther you are from the center. So cutting the mass in half should make the speed smaller, the escape speed smaller, and then cutting the radius, or doubling the radius, should also make the escape speed smaller. So the escape speed for Earth was around 11,000 meters a second. So the answer for part 9 should be less than 11,000 meters per second. Just in case you get some number bigger, if you get a number bigger than 11,000 meters a second, you should be thinking, oh, something's wrong here. And for those of you with children who need your attention, you say, wait a second, I'm doing physics right now. It's not family time. Because they should grow up knowing physics is more important than everything else.
I try to tell Jocelyn, and she says, I'm not even gonna remember that by the time 5th grade, let's just eat.
That's why you have to keep telling me.
I was watching Paw Patrol and the vehicle stops midair to change. I'm like, that's not possible in physics.
There was a very short-lived TV show in the 70s called, I think it was Automan, something like that. And there was one thing that I do appreciate, is that the car it was kind of like a spin-off of Tron, but this car took a right turn, and there was someone in the passenger seat. When the car took the right turn, the person in the passenger seat, it was a right turn. The person in the passenger seat basically got plastered up against the window. And I appreciated the fact that they at least maintained that aspect of physics. Although if it was a sharp enough turn, his head would have splattered.
Careful.
It was a family show, so, you know. Like Game of Thrones.
So we just understood that because the forces are either multiplied, not the force, but the gravitational force. What is it called, a constant?
We cut the mass in half,
Cut the mass in half,
and we doubled the radius.
and that made the escape speed slower.
Yes, it can't take as much effort to get away. Because when we double this, we're farther from the center. When we cut that in half, there's not as much pulling us.
Farther from the
All right, other questions on 9?
What was the unit speed?
It's an escape speed, it's a speed. Therefore, yes.
What she said?
I would naturally assuming that if I can hear what people are saying, that everyone else can hear it too. I'm assuming I have the worst hearing in the world. So,
Don't assume.
don't. I think it's the kids that did it to me, but, you know. I had no gray hair before they were born. A couple of nods from parents, I think. All right, number 8. came in with a box. I had a box in my hand at one point. And since I'm not seeing the box, I'm gonna go back to my office and put it down.
Hopefully they.
I'm gonna go back to the office and grab the box set I had, and we will talk about number 8. I'm just gonna leave the recording going. All right. So number 8, where a launcher shoots a ball horizontally from a height of 1.5 meters. It lands a certain distance away. In other words, the horizontal distance. How fast was the ball launched? So let's actually go through an example here. All right, because these things were both made by Pasco, there's a bolt on the other side of this that slides right in there very nicely. It's designed for that so that this stays attached. Now, some of these have a plumb bob hanging down here, so you don't need this. So you can actually figure out what the angle is straight from here, but the string broke on this one, and so I have to do it this way. It's a little off 0, so let me adjust. Now notice when I let go, the thing is going to fall backwards. The center of mass has shifted so that the center of mass is no longer over the base. And so to offset that, we grab a clamp. Now, we have not done any labs with the projectile launcher. I think that was the other group. Okay. So basically, we're going to put the ball into here. It's supposed to come with 3 over time. We seem to get fewer and fewer. So I need to put it into this. And just to give you an idea of what's going inside here, I'm going to trust your eagle eyes. Can you see the little bit of yellow in there? I might not have the right angle for every person in here, but there's some yellow right inside there. All right, so Lacey can see it. I guess you two are the farthest away. You see it? Okay. How close do I need to go? There's a little bit of yellow right inside there. And I guess you were the next farthest away, seeing the yellow? Yeah. Okay. That gives me an idea of where the ball has been, or how this thing has been cocked. So I put that in there, I use the ramrod. That's 1 click. So right now, I'm pulling the ball out just so that it doesn't accidentally fire. So right now, that yellow thing is right next to this thing that says short range. If I click it again, it'll be medium range, and then it'll be long range. And later on, you will have experience with this, and you'll see the yellow mark. I'm going to do this for short range, just for the demo. Now, I've done the story of the kid in Richmond who was killed from my youth. I talk a lot about childhood scars. This is one that I still remember from my childhood. There were some kids who were playing with a Nerf ball. I'm trusting you know what Nerf balls are.
Mm-hmm.
All right, and they wrapped it in aluminum foil and were throwing it at each other, and one of the kids got hit in the temple and actually, it's just one of those freak things, died. So this using a projectile launcher, probably the most dangerous thing that we do. It's not dangerous if you're just careful and you're looking out for it, but if you are walking by, try not to walk in front of it, or if somebody's walking in front of it, don't fire when someone's walking in front of it. And don't start looking down the barrel while it's loaded. True for anything that shoots. Now when I pull it, it actually does matter how I pull it. If I pull it quickly or if I pull it slowly, I'm gonna get different answers. So whatever I'm doing here, I need to be consistent as possible. I'm gonna do a quick pull, and at least so some people can see. And also so I can hopefully block it from going out into the hallway. And creating a little bit of a fire hazard. All right, didn't go particularly far there because it's on the short setting. So what I want to do is figure out how far does it actually shoot. So so I need to know what the height is, and I need to know how far it actually shoots. Well, the height's simple enough. Before I do that part. If you'll notice right here, there's a little white circle. That white circle is where the ball is, that's the position of the ball when the spring is gotten back to equilibrium. So when you're trying to figure out how far does the ball go, well, the ball goes, basically that's the position of the ball when it's launched. That's when the spring is no longer exerting a force on it, and then however far. So when I'm measuring the height, since the bottom is going to hit the floor, I'm going to measure the height to the bottom of the white circle. Okay, one click, it's now on the short setting. And I think it's off 0 degrees now. We'll stay in 0. I push the ball in so that the ball is right up against basically the plunger. Let's see, the height from which it's being shot. It's like 101.4. So height. And now how far out does it go? Now, ideally, I would have pick the one that is not, it is shrinking here. I'll put my foot on there. Now I'm gonna eyeball this one. In a lab, you would want to do better. And also where it hits, it's really nice if you put a piece of aluminum foil down, you tape the aluminum foil down, and it's gonna hit the aluminum foil and leave an indentation so that you know exactly where it hits the ground. We're not gonna be that sophisticated at the moment. So I'm going to eyeball this for now, and we're going to eyeball where it hits. So I guess Isabella and Brianna, and I guess John G and Amina, you four have the best view of where it's going to hit. So we're going to see how well 4 of you agree on this. All right. keep that where it is. I got 4 markers here. Step down. All right. So Nina,
Back a little bit, I think I'm right with you.
all right, Janji,
There.
Isabella,
I look at that red spot in between.
that one,
I'd say in between so like 5 hertz.
right here. It's nice because I saw it somewhere around here also. All right, so the mid spot, it looks like it is somewhere around 139. So we'll just go with that for now. And now it doesn't move. So the distance, 1.39 meters. All right, so because the first part of the problem is how fast is it launched? So we have enough information here. Now, when it is launched, we first have to figure out how much time is it in the air. Now, using a stopwatch is going to be really impractical because it's going to be less than a half second, and under a half second, reflexes become really a dominant influence there. And so we need a better way than just timing it. You think you can do it? Was that, no, what? I was going to avoid the timing, but if someone thinks that they can time it, we can test it against what, closer to what it is. Anyone want to go for it? Good. Was that a yes?
I'll time it.
Oh, right. All right, from the moment I pull to the moment it hits the ground. So I'm gonna do 3, 2, 1, pull. When I say pull, I'm gonna pull. 3, 2, 1, pull.
It was 1.61.
Feeling confident with that?
We can do it again.
Anyone confident with what he just said? Three, 2, 1.
I got something different. I got 0.60.
And this is part of the issue here, the fact that for the same experiment, he's off significantly between the two. And that's probably enough. We'll now see what science says. And let's see how well this demonstration works. Even though I did think I did something similar. So I'm going to drop this at the same time I shoot this. So I guess the question, is this at the same level? Is it the same level as the barrel here? Up a little bit. There. 3, 2, 1, go. They hit roughly the same time. Part of that is my own personal reflexes there. So if we can figure out how much time this takes to fall, we know how much time that one is in the air. Well, it's starting from rest. It gives us some formulas for that. I know that the distance it will fall is equal to 1/2 GT squared. This is from chapter 3. G I know. That's 1/2 times 9.798. I'm trying to figure out time, and I know H, 1.014. So I guess we'll do that first. So 1.014 equals half that. 34.899.
899.
All right, we're trying to solve for t squared, so what's next? I heard somebody say it softly.
Divide by 4.8.
I heard that one more loudly. And so on my right side, I left with t squared, and I'm equal to whatever that fraction is. 2 something.
20698.
So now I need to get the t, so how do I get rid of that square? I assume that was your hand gesture, Brianna? Okay. So t is equal to whatever the square root of that is. 4539? 49. 4549? Units? Luis's reflex is much better in the second one than the first one. So it's in the air for less than half a second. And so we're trying to figure out, how fast the thing is going. Again, because once it's launched, after it's launched, it's in the air, what are the forces acting on it?
Wait.
And?
Normal one?
Acceleration due to gravity.
Acceleration due to gravity, not a force. I heard normal force. If there's a normal force that's touching something, what's it touching?
Just wait.
Yeah, just wait. If you throw in air resistance, yes, there's air resistance, but we're going to assume that's not significant. And that force is downwards. Since the only force acting on it is downwards, the acceleration is downwards. Which means that the change in velocity only happens downwards. Which means there's no change in the velocity horizontally.